Hey guys, so we're finally starting calculus unit. We're off from the review. So one of the things I hope that I do in class is show you that on AP Central, they do their own daily videos. Now, I have not introduced you to them yet because they don't do a review unit. They start their unit 1 with limits and continuity. So I'm saying this to you now because that's what we're doing. So if you go onto your AP College Board and you go into our classroom and you'll see the units, there is a daily video. And everything that we are doing in our unit 1, those videos are good to watch. They're very short, but the great thing about them is you have AP teachers and graders that actually go through some multiple choice questions with you about the topics we're learning. Now, of course, our topics might be a little bit longer, a little shorter than they do it. So I'll try to keep you informed with which videos that it would be great for you to go through if you have the extra time. All right, so right now we are going to go through limits and continuity. So limits we've done before when we talk about end behavior, right? The idea was that a limit is as x approaches some value, okay, some value, but in the past it's always been infinity or negative infinity. Where is it going? What y value is it going to? Okay, so we are given the x value and we want to know what y value. In the past, when we did end behavior, I would say as x goes to negative infinity, our graph is going down to negative infinity. But now we're actually going to do limits from any coordinate point, okay? So the one thing I actually want to start, even though it says 1 through 5 and stuff here, I actually want to start with function values, okay? Because this is what we know how to do. If we weren't given a graph and we were given a function, that would tell us to evaluate at -4. So plug in -4 and tell me what you get for an outcome. But this time, because we have a graph, what I would do is go over to -4 and find exactly where our coordinate is at. And as you can see, our coordinate is at the value of 1. For 9 here, okay, I'm going to -1. And as you can see, our coordinate, now this is a whole, so that doesn't exist. Our coordinate is at the value of 1. At 2, there is a hole and nothing else. So at a hole, it does not exist. Our value at 3 is an asymptote, which means our graph never gets to there. So it does not exist. And 5, if we look at 5 right here, we have a jump, but we do have a filled-in point. So our value is 2. Okay, those are things that we've done in the past. Now, when we think about limits, so this is the exact point. Where limits, what did we read above? It was about approaching. So remember that limit is approaching. It doesn't have to be there. We're just talking about approach, okay? Now, when we talk about approaching, it must approach from both sides to the same value. And what I mean by that is that if I said, and you'll see in 6 and 7 here, if I say limit as x approaches, and I'll take number 1 here, -4 from the left side, I would put this little negative here. So this means left side. And then when I say limit as x approaches -4 to the right side, you would have that little plus. The idea is if I just say limit as x approaches -4, I must be saying that both of these equal. Okay? So they have to be from the same side. And that will get more clear down here. Okay, guys? So if we look at -4 right now, I look at -4. I don't care what that value it is. I care about where it's approaching. So as you can see on the left side, and I'm going to use marker here, see if I can show you. From the left side, I'm going to 1. And from the right side, I'm going to 1. So they're approaching the value of 1. Here is the issue with number 2 here. We're asking as x approaches -1. So if we are to follow our graph, and I'm going to use a different color, and we approach, we're on our graph, and we're approaching from the left side, I'm right here. And if I approach from the right side, I'm right here. And what value did both of those go to? Both of those sides went to the value of 4. Now, of course, we know that at -1, it is 1, but where it's approaching is 4. So see the difference? Let's look at 2. So again, I'm going to grab another color so you know the difference between them. I'm going to pause so I know what I just did. Okay, I fixed it. All right, so again, we're at limit x approaches 2. So from the left side, I'm right here. From the right side, I'm also going right there in the same direction. And as you can see, it's the value they're approaching is 1. So even though it does not exist right there, there is our graph is approaching that number. All right, 3. So if we look at 3, of course it's an asymptote, so it does not exist. But if we look at where it's approaching, from the left side, our graph is going down. And from the right side, our graph is going down. So both sides are and did I not pause? Probably not. Of course, it's recording during this. Technology issues, guys. Okay, I'm going to try not to hit the computer anymore. Okay. So they're both approaching down. Well, what's the value as you go down? It's -infinity. But here's another thing to keep in mind. -infinity is not a value, right? We can never get there. So you could say does not exist. Either one of these is correct, and you need to be prepared for both of them because on a multiple choice, you don't get to choose which one appears, okay? Now, 5. This is where I'm actually going to go down here first, and then we're going to answer this one. Because remember, a limit that doesn't have that plus or minus there means that both sides need to go to the same thing, okay? So if we look here, we look at number 6, we have limit as x approaches 5 to the left side. Let's see if I can get a marker right now without touching my computer. So from the left side, I see that my graph is approaching the value of -1. Okay. From the right side, so look at 5, and my graph is right here. It's approaching the value of 2. Okay, so left side, right side. Now, because these two values are different, that means the limit at 5 does not exist. We have a value at 5, but the limit from both sides do not approach the same thing. Knowing the limits actually allows us to graph in the long run because we talk about continuity. Knowing that it exists at 5, but the approach does not happen, it means it's a jump. Whereas if we know there is a limit in approaching, but the actual value does not exist, we know it's a hole, or it could be an asymptote. Okay, so that you have to keep in mind. So let's talk about continuity. Informally, a function is continuous where it can be drawn without lifting a pencil, okay, or your finger. I like tracing it with my finger. And anytime I have to lift up my finger to get back on the graph, that is not continuous, okay? So the other thing to think about it as it's connected, okay? So the idea, that's the informal, is continuous where it's connected. Okay, but here's the formal definition. It is continuous where the limit and the value are the same. So in other words, if we go back up here at -4, our limit and our value is the same, so it must be continuous. Right here for number 2, our limit and our value are not the same, so it's not continuous, discontinuous. So there's different types of discontinuity that we are going to go through. Right here, it's a jump, a hole, okay, and goes back and forth. And like here, it does not, technically it's not the same, right? Because negative infinity, it does not exist. So asymptote, we have our hole, so on and so forth, okay? So now they write a definition. This is the formal way of actually in mathematics writing that the limit from both sides equals the actual value. So remember, this is approaching left. This one is approaching right. And this one is the exact. So when all 3 of these are the same number, it is continuous. Okay, so here we're going to get into the different types of discontinuities. Okay, so we have holes, vertical asymptotes, and jumps or breaks. Okay, the 4th type of discontinuity is an oscillating discontinuities. These really don't happen or rarely do, but you can see it right now if you graphed sine of 1 over x. You'll see how that works, okay? And you'll see it gets really, 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 really close. So on the graph itself, it looks like it connects, but it really doesn't. Okay, so now let's talk about here, let's list some discontinuities from above. So if we look at number 13, example 13 here too, we're going to go back up here and we're going to say which of these, and we kind of already did that, right? Do not equal. So here we have a continuous, but at -1, these are different. So -1, so we have a discontinuity at -1. We have a discontinuity at 2. We have a discontinuity at 3. And we have a discontinuity at 5. Okay, now we are going to describe these as removable or non-removable. Okay, and this you will have to memorize, guys. So removable discontinuities occur when it has a limit. Okay, so in other words, holes. Okay, if it does not have a limit, okay, then it's a non-removable. and those are usual jumps or vertical asymptotes. Okay, so let's talk about which okay, so I'm hoping this is being recorded and we'll go from there because I might have to do this all over. Okay, which of the following from example 3 are removable? 13. Now, why it says example 13 is because these are the discontinuities. So our answers can only be -1, 2, 3, or 5, okay? So if you look, removable or wholes, that means the limit exists. So if you go back up to your examples of limits, which numbers exist, what happens? So if you look, our limits that exist from these 4 things, oops, down here, are x is -1, because at -1, that limit is 4, and x is 3, that limit is 1. Okay, 4 and 5 do not exist, or it's an asymptote or jump, so that's why it would be non-removable. All right, let me do this one. Okay, at x values where a function is continuous, limits can be found by direct substitution. So one of the things you'll learn as we are doing this, we're going to test out a limit, especially if you don't have a graph, by plugging it in first. Okay, so if I plug it in first, I would get 3 times 3 squared plus 2. Now, when we calculate that out, we get 29. So the limit at 3 is 29 as it approaches 3 is 29. Now this one, if we plug in, we get 1 squared plus 1 all over 1 plus 1. So when we simplify that, we get 2 over 2, which is the value of 1. So the limit as x approaches 1 is 1. And now we plug in, so we would have cosine to x, or not x, we're plugging in pi over 3. Think of your unit circle. If you go to your unit circle, you go to your first part of your coordinate, you would get -1/2. Okay, so direct substitution is usually your first step, always. Okay. Now, piecewise. So with piecewise, be careful that you are doing the correct side to it. Okay. So when we look at if f of x equals 4 minus x when x is less than or equal to 1, and then 4x minus x squared when x is greater than 1. What we actually have to do is check both sides, because this is where our graph splits. Okay, so when our limit is to the x value where it splits, you have to test both sides. So we're going to go limit as x approaches 1 from the left side. Now when we do the left side, it's going to be above here. So we say 4 minus 1, which equals 3. Now we have to test the right side. So limit as x approaches 1 from the right side. So this would be 4 times 1 minus 1 squared. And what do we get? We actually get the value of 3. Now, because they go to the same place, that means the limit exists, and it goes to 3. Okay? Now, here again, we are approaching where the graph splits. So I have to test both of them. Okay, so I go limit as x approaches 1 from the left side, which would be 3 times 1 minus 1 cubed. So we get the value of 2. Now I'm going to test from the right side, which is limit as x approaches 1 from the right. We get 2 times 1 squared minus 1 equals 1. Since these two do not equal the same, this limit does not exist. Okay? You only test both when the number we're going to is where the graph would split. Because as you can see in 20, if we use G, so we're going to use this one right here, it says -1. So when you're using -1, you're only caring about less than 1, so you're only caring about the top half. That's where -1 exists. So all we're going to do is plug in our -1 to that top equation. Be careful of your negatives. Now when we do that, we get, oh, I put 2 equals in a row. We don't want to do that. That's bad for notation. Put it underneath, and we get the value of -2. So see how I do not have to go left and right, because it's not where our graph splits. Now this, I'm going to show you the graph to this, but we are not going to focus on these functions. This is the function that exists, and it's really interesting, but it never really, like if it comes up on an AP test, it's going to be like 0.002%. Okay, guys? This is called a step function or the greatest integer function. What happens is its notation looks like L's on both sides here. So it's not brackets, it's not a full bracket, and it's not absolute value. So keep in mind, when you see that come in there, I want you to ignore the question. This function looks like steps. Okay? And then there's a little tricks to it, because if you go by as it approaches on this one, I'll show you this one, as it approaches 1/2. So if you see right here is 1/2, well, from both sides, where does it approach? It approaches the y value of 0. Whereas when it approaches 1, well, if I go to the value of 1, 1's right here, your left side does not match your right side, so it does not exist. From a graph, this is pretty easy to see, but I'm not going to have you guys graph those. So anytime that you see this function, I want you to cross it out and don't worry about it. All right, let's try some of your limit stuff. Be careful on your notation, and we'll go through that in class.